I'm going to talk about three terms that are useful when describing the graphs of trigonometric functions. All right? Let me start by drawing the graph of a certain function, and then we'll continue. All right, almost done. Okay, so this is not the graph of a trigonometric function. However, this graph will allow me to introduce the three terms that I want to focus on. Okay? Now, would you agree that this graph can be described by a certain portion that is copied over and over again to create the graph? Okay? If that's not clear, let me put a red rectangle around the portion that I'm referring to. All right, can you see that if I copied the portion of the graph inside that red rectangle, if I made lots of copies and I put them next to each other, that I could recreate the original blue graph? Okay, so not every graph of every function, not every graph has this property that it can be described by several copies of the same piece, okay, over and over again. However, for graphs that do have this property, we can define what's called the period. Okay, the period is the width of that piece that we make copies of. All right, so the distance from one end of the red rectangle to the other, that's called the period. And that's often denoted by the letter T. All right, so can you see that for this example, the period has, the period, or the width is equal to 4? Okay, so we can say for this graph, t is equal to 4. Now, notice also that there is a maximum and a minimum y value. Okay, again, not every graph of every function has a maximum or a minimum y value. All right, not even every trigonometric function has a maximum or a minimum y value necessarily. Okay. However, the ones that have a period and they have a max and min y value, for those graphs we can define what's referred to as the amplitude. The amplitude is the farthest distance from the center line of any point on the graph. Okay, so if I measure the distance from the x-axis to the top of that peak, that is referred to as the amplitude. Okay, and that's often denoted by the letter A. So for this graph, for this example, can you see that the amplitude is equal to 5? Okay. Now, when you compare a graph that has a that is shifted horizontally with respect to another graph, you can define what's called the phase between those two functions or those two graphs. All right. So let me show you what I mean by that. Let me draw a horizontally shifted version of this graph. Okay, so for every point on the blue graph, there's a corresponding point on the green graph, right? The distance between corresponding points is what is referred to as the phase. So for example, if we measure the distance between the bottom of these two valleys, okay, that is the phase. And that's often denoted by the Greek letter phi. Okay, so between these two graphs, the phase, or phi, is equal to 2. All right? So let me repeat what these three terms refer to, and then I'll have you do an example. Okay? So if and only if a graph can be interpreted as a piece that is copied over and over again, then we can define what's called the period, which is the width, right, the horizontal distance from one end to the other of that piece. Okay, if it has a max and a min in the vertical direction, we could measure the maximum distance from a center line, and we define that. We call that the amplitude. Okay, and if we compare two graphs that are horizontally shifted with respect to each other, then the distance between corresponding points with respect to those two shifted graphs, that distance is referred to as the phase. Okay? Now, let's do an example. Or let's have you do an example. As before, give me a little bit of time to draw a picture, to draw the graphs of two functions. Okay, so almost done. All right, so I've drawn the graphs of two functions, and one of those functions can be described as the transformation, a transformation of the other function. Okay, the transformation involves a horizontal shift. So I'd like you to pause the video and determine the period of the two graphs, the amplitude of the two graphs, and the phase between the two graphs. Okay? So pause the video and do that now, please. Okay, so I'll go ahead and work it out now as well. So both graphs can be described as generated from multiple copies of the same piece over and over again. This is referred to as, these two graphs are referred to as square waves. All right, so the piece within that red rectangle, copies of that piece will generate both graphs. So the width of that rectangle defines the period. And for both graphs, the period is equal to 8. All right? And the distance from the center line, in this case the x-axis, to the highest point defines the amplitude, which is equal to, for this example, 7. Okay? And both graphs, if you look at one point on any point on the blue graph and measure the distance to the corresponding point on the other graph, then you can determine the phase. So in the picture it's that distance, and the phase here is equal to 2. Okay? I hope you got those numbers. Now let me make one comment about amplitude that that might be helpful for certain graphs. Not all graphs are centered with respect to the x-axis. Okay? You can still define an amplitude by identifying what's called the center line. All right? So, for example, suppose you were analyzing the graph of, or the following graph. Give me a second to draw it. All right, so that graph is not centered with respect to the x-axis. All right, however, it's clear that that graph is centered with respect to the horizontal line, which is denoted by this purple line. Okay, so even for this graph, you could define an amplitude as the distance of the point from that purple line that is farthest from the purple line. Okay, so for this example, the distance I've drawn there, that would be the amplitude A. All right, so the amplitude is, what I'm trying to say is the amplitude is defined with respect to what's called the center line, which cuts through a horizontal line, which cuts through the graph in the center, but the center line doesn't necessarily have to be the x-axis. That's the point I'm trying to make.